Okay, let's continue with the second part. Yes, can feel the air conditioning. Yes. And let's rock and roll.
Okay, so last time I showed how the free monoid on two generators can be used to build the Kuntz algebra O2 by using basically the Cayley tree, which is just the usual rooted binary tree. So I want to start today by looking at sort of that led us to sort of this directed graph picture of building O2. Today I want to look at a different way of getting it, which generalizes in a slightly different manner. Looking at the free monoid just as a monoid, how do we use that to build the Caesar algebra? Okay, so that's sort of the basic question to start with. So what should be put in quotations universal and I'm going to be a little bit more specific, let's say a submonoid of a group. A little more restrictive than necessary, but that's what we have in the case of the free monoid. So the intuition should be taken from the left regular representation. So
And here you mean in the convolution sense, the universal Caesar algebra.
I think it'll be clear. It'll be clear in a minute, but I don't really need to say convolution at the moment. So yeah, no, I'm not really looking at it quite that technically. So I'm calling it pi sub L, the left regular representations. This would take F2 plus. Okay, I was doing well for 2 lines. Now I'm in my trouble again. Of course, this takes pi L. The word alpha acting on the basis element corresponding to word beta is just so what do we know about this? Okay, so first of all, the image of F2 plus sits inside the isometries on H. Let's see, you can't fill in things that you've started. Right, so this is a representation by isometries, and of course it's a representation. So pi L of alpha beta is a composition pi L of alpha. Oops, L. Now, if we're looking at groups, we would have unitaries, homomorphisms, and that would be everything we want, right? So this universal Caesar algebra will be universal for unitary representations of the group. But it turns out that for monoids, that's not enough. So in fact, Nika observed this. Pi sub L preserves reverse more structure. And I think his intuition came from this example of the free monoid and O2. But it's also interesting that Murphy actually wrote a paper studying just the universal C-star algebra determined by representations by isometries.
I mean, Gerard Murphy.
Gerard Murphy, yeah, and it was a huge mess. So, of course, for the natural numbers, he got the right answer. But for, say, the natural numbers squared, he got some vast non-amenable non-nuclear structure. So it's clearly somehow the wrong picture. And what was missing was the observation of Nika. And let me explain what that was.
And can you say again what delta beta is? What delta is?
Oh, so these are, so for beta in the monoid, these are the standard orthonormal bases for little L2. Right, so these are all sequences indexed by the monoid that are square sum.
Oh, yeah, sure.
It's just the standard orthonormal. Yeah, some people write E sub beta, but E is such a fraught letter when you're dealing with graphs that I thought I switched something up.
The alpha and beta just words in two letters.
Yeah. So the key thing is that this free monoid as an order. Namely, very naive, right? So word alpha we think of as less than or equal to any longer alpha beta. This, if you think of these words as being elements of a directed paths in a directed graph, we're just saying that one extends the other. That's always been my intuition. But this is very common to have this kind of order on a monoid. Moreover, well, let's see. So, and now how am I displaying this? So for any two, so if we look at all the extensions of alpha, okay, like that is alpha multiplying the monoid, with all the extensions of alpha, and we intersect it with all the extensions of beta. And this would be the common extensions of alpha and beta. So if this is non-empty, then back there is a gamma, this intersection is actually all the extensions of gamma. So am I calling this? Yeah, so this property.
And gamma is equal to alpha or beta, depending which is longer.
In this case, the only way this could happen is if one of them actually extends the other and then. So this property that, okay, so I'll introduce the standard terminology from inverse semiconductor theory, or probably other places too. So a set like this is called a principal right ideal in the monoid, because that's exactly what it is. So this says that if the intersection of two principal right ideals is non-empty, then it's equal to a principal right ideal. And monoids with this property are called right LCM. LCM stands for least common multiple. So they have a least common. And we'll see variations on this idea a little bit later. Okay, so now what does this mean in terms of this left regular representation? We interpret it in terms of the range projections of isometries. So I'm going to write out range projections. So this takes, I think I'm doing a little bit better than I did on Monday in terms of having the writing clear. I'm not hitting the button so often, but it is going much more slowly. So bear with me. So if we look at the range projection of pi L of alpha, that would be pi L of alpha times pi L of alpha adjoint, the range projection of the isometry. And we multiply it by the range projection of pi L of beta. Then this really says that that's just pi L of gamma range projection. And I suppose I could say or it's equal to 0. Like, I don't want to write the whole thing all over again. Let's just say if alpha is going from, and just interpret this perpendicular sign as meaning that the intersection is empty, no common extension. So let me give a name to this equation. Am I calling this one star? No, somewhere in my notes I had a star, so I'm going to call this one double star. But if I forgot to make one with star last time, then this is sometimes called Nika covariance. And that's the key property, right? So the Hopeless algebra.
Sorry, Chuck, I just missed it. So the sort of orthogonal sign means that neither alpha nor beta extend, right?
That's right.
Okay.
That's right.
I will check.
I actually use that notation in a more general way.
Okay.
In the
path.
But I'm not going to introduce it in these talks because there's a for it, except that I needed a quick way of writing this. But yeah, it just means that this intersection is empty.
Okay.
Sometimes I use the double intersect symbol to mean that an intersection is not empty. That's actually notation due to really excellent. Okay, so this we talked about this last time. But you might say this is the definition. This is the universal. Well, let's call it. Algebra is universal or isometric representation by isometries. Satisfying this covariance. So this is the extra structure that we can see in the left regular representation, which characterizes the correct representations of the monoid. So this is the idea that I want to talk about some more. So as Piotr mentioned, this free monoid has an even stronger property than right LCM. It actually has the property that if the intersection of two principal right ideas is not empty, then in fact one of them is actually contained in the other. So I'd like to talk about another example where that doesn't necessarily happen. So these are the bounce-like solitar monoids. This is a new example. So we let C and D. Should we make it look like a D? Non-zero numbers. And the group bounce-like solitar group, I'll just refer to as BS, corresponding to C and D, is defined to be the group presented by two generators, A and B, such that A, B to the C equals B to the D. I think you're going to have to just believe that the symbol is what I say it is. A famous family of groups, in fact, and lots of really deep stuff is known about it. So I may be scratching the surface of it here. It turns out that we can move the B to the C and B to the D to the opposite sides by using inverses if we like. So if, say, C and D are both negative, we can have an equivalent relation by just moving them to the other sides. That would be A e to the minus C equals B to the minus D A. If say one of them is positive and the other negative, let's say, for example, that C is negative and D is positive, and we have that's a comma, we have an equivalent relation length. So we would move this to the other side. We would have A equals B to the D, A, B to the minus C. The point is that we can always rewrite this relation using only positive exponents. And that means that the group has a positive presentation, and therefore there's a natural monoid we can find by using the same presentation. Okay, so we defined the monoid. It's let's see, BSCD plus. So the usual way of writing this is, okay, so we have to write A, B to the C equals B to the D, A. Say if C and D are both positive. Wow. Now I've done this, what I did to the coffee machine, I've done to the screen. Persistent letter. Okay. We can handle this old school. And we write down A is B to the C minus C, A, B to the D. If, say, C is negative, and D is positive. And then we write a plus here to indicate that we're only using words that use the generators but not the relations. And it's a fact. This is not so hard to prove in this case. And there's lots of results about when this kind of thing is true, is that this monoid actually does sit inside the group. It's not always true for the present, but in this case, it's true. Let's see. Okay, so what did I want to say about this? So here's the theorem. So let me call this monoid. Capital lambda. That's gonna be my letter for things that we're studying in general. So let's just give it a name so I don't have to write this down. So first of all, lambda is right LCM. So it has this property. If two principal right ideals in lambda have a non-trivial intersection, then the intersection is another principal right idea. In general, we don't have this graph-like property that in that case, one of them must extend the other. So definitely it's not that point. But there is sort of an interesting variation on that. In this second case, so if it's the case that, say, C was negative and D was positive, then we do have that property. So alpha lambda intersect beta lambda non-empty implies either alpha is an okay, so it's not completely on the fritz. Alpha is an extension of beta, or beta is an extension of alpha. So we get this graph-like property in this non-oriented case. But what we're getting out of this, well, let's just say that lambda is not at all like the graph. So this is actually, I think this is quite strange, and I still don't really know what this, if this means anything, I don't know what it means. It's a kind of funny observation that came out of analyzing these monoids. Okay, I'd like to show you one more example. This. So I'm going to make a very specific example, but you'll see that there's a whole family of examples of this type. So let's I'm going to draw give you two vectors in R2. So V1 not n equals -1, comma 2. I just get hasty. Right? And V2 1, comma 1. And let's define a cone C. Be all non-negative linear combinations of these. So C1 V1 plus C2 V2, or C1 and C2 are non-negative. And then I'm going to define my monoid lambda to be the intersection of that cone with the integer lattice. That's my monoid. So it's an abelian monoid this time. So I want to try to draw the picture. Let's see what happens. I'm not going to draw the whole thing, just.
And C1, C2 are what, integers?
No, real numbers.
Real numbers, okay.
Okay, so yeah, so. Right, so we have a certain cone in the plane, and we intersect that cone with the integer lattice.
Okay.
Countable one. Okay, so
So
bear with me for a moment.
so even if lambda is if you have an element of lambda, then this linear combination can have rational coefficients, rational non-negative coefficients.
So the C1 and C2 can be any real numbers.
Yeah,
But if we take such a thing, if it's, yes.
in this intersection.
It's possible that C1 and C2 are not integers. In fact, for sure, surely they will not always be integers in order to get points in this. Yeah, that's true. It's not really a very complicated monoid. No, I mean, I'm not hiding something really secret here. It's just. So I would like to draw it. So let me, it's going to be very fraught with. I don't need too much of it, but I need several levels. And I'm hoping that it'll be enough to see what goes on.
And you can use color if you want.
I'm going to use colors for drawing the cone. Oh. Okay, so V1 is 1 to the left and 2 up. So it goes through this point. One. They're not very square. Very badly drawn, sorry. I hope what I want to show you is visible. So now let's let alpha equal 0, 1 and beta equal 1, 0. Whoops. It is not in there. What am I talking about? Well, so I didn't do this example carefully, did I? I think it'll be okay if I let beta equal 1, 1. So that's laid plans and all. So here's alpha. Here's beta. Let's look at the principal right ideals corresponding to those. So I want to look at alpha plus lambda intersected with beta plus lambda. Now I'm going to try to say alpha plus lambda, I have to go so 1 over up 2 and then 1 over up 1, 1 over up 1. This is maybe we can do say red. I have to go over 1 up 2. And then I'm just going to continue here. So the intersection of these two principal right ideals is built from the cone base at this point. We've got the red ray to the right and the blue ray to the red ray to the left and the blue ray to the right. And what can I say that so maybe I'll do one more color. These two elements of lambda generate the intersection. But there's no single element of lambda that generates the intersection. So let's call this gamma and delta. So this is equal to gamma plus lambda union delta plus lambda. But it's not a principal right ideal. This lambda is not one of these right LCM groups. I think it's the most it's more sort of the most elementary example I know of this kind of phenomenon. Okay, and I'm going to come back to this idea a little bit later. So now I want to address the question of what's the common thread in all of these examples. More importantly, last time I began with the key idea that from whatever combinatorial object we start, we have to extract some likely compact Hausdorff space that'll be the analytical basis of the C-star algebra. So we have just a countable thing, and we have to build a real topological space from that. So I want to describe how that goes. And I think I'm going to begin back with the case of a directed graph. So let's see, so in all the examples, I'll define I'm saying the, but there could be others, locally compact Hausdorff space. So I think the best intuition for this comes from the directed graph case. So let's take a look at that again. So last time we used this notation E star for the finite directed paths. And now I'm going to introduce a couple of sets. So I call it script early, well, capital script E upper 0 is all the principal right ideals. So alpha E star. Of course, this means all the finite paths whose initial portion is alpha. And then we do what they in more abstract setting they call form the Boolean closure. I'm going to denote that by just the capital E. And this is the set of all differences of such sets in the following way. So we look at, say, things to the form alpha E star minus a union, say, I from 1 to K of beta I E star. Here, the alpha and the beta I's are also elements of E star. And then I'm going to let script capital A be all finite disjoint unions of sets from this script capital E. So disjoint union A equals 1 to say M EJ. The EJ's 1 to E. So then it's an elementary exercise that holds more general. And A is a ring of sets generated by E0. Just start with the principal right ideals. That feels like a very natural thing to begin with in this context. Generate the smallest ring of sets you have that's described explicitly this way. Moreover, it's invariant under these partial bijections we have, namely, just concatenation with a fixed element that we used before. So this is somehow very naturally associated with our stuff.
So I have a stupid question. When I look at this E0, isn't it the same as the set of all subsets of E star?
No, it's only certain subsets. So this is
But isn't alpha running any finite path?
that's right. But for a fixed alpha, this set is all the finite paths that extend alpha.
But if I choose any alpha and any path, don't I get any path?
So
It's one-sided.
if you take any beta, alpha beta belongs to this set.
Mhm.
This is so the singleton set alpha might not belong to E0. Or take an arbitrary.
Oh, yes, of course, because yes, sorry, yes, of course.
There's subsets of E star of a very special structure.
Yeah, I mean, all these sets are typically not singletons unless you have a very short graph.
Oh, so now you could
Okay.
so if the source of alpha has only finitely many edges coming in, you could throw all of their successors away and get a single.
Yeah. I see my mistake. Yes, thank you.
Yeah, but again, they're still very special.
I have a question about
Yeah.
the meaning of K in the definition of E.
Oh, it's just a finite number. And K is an arbitrary finite number. Let's see, so I should put that here. Am I interpreting your question correctly?
Does the empty set account as a finite path?
Shouldn't.
Well, so in this case, if we throw away the empty set, that's okay, right?
For example, does E star belongs to our E0?
Yes.
It's the same thing as asking
I see.
empty.
No. No, I'm not sure how important it is, but I have not included E star in.
Okay.
And really, the reason is the following. These sets are fibered over the unit space of the graph. Right, because the range of alpha is the same as the range of all the elements of this ideal. So we could really index these by, if I like, by a vertex of V. If I put V here, and now this is not readable anymore.
But it might happen that if you have just one vertex, that E star is a subset of E0.
Okay, yeah. But in general, we shouldn't.
No, in general, we should, but no, yeah. have a Kunz graph, of course, yeah.
Right, and so the point is that we're sort of, all of these themes are filtered by V, so there are as many rings like this as there are vertices. And if there are infinitely many vertices, and we run it's not useful to consider all of them together. It's really what we're going to get from each vertex is a compact Hausdorff space. And we should be getting a disjoint union of those. So we really want to get a locally compact Hausdorff space if we have an infinite vertex set. That's why it's best not to include all of E star. But certainly V E star is in there. So any
So in general, E star belongs to this collection of set A, if and only if the locally compact space is actually compact.
Correct. But it happens if and only if the vertex set is fine.
Okay.
Exactly right. Exactly right.
Unitality of, yeah.
The total thing is obtained by taking this finite union instead of, yeah.
So now where's our space? So we let X, this is actually standard. I found this in Kelly's topology book and due to Stone. Building spaces from this kind of algebra sets. So X sub E is the set of ultrafilters in A. Now, again, I should point out that for different different vertices, the rings we get at those vertices are disjoint. So each ultrafilter really belongs to a particular one of these corresponding to a vertex. Maybe I should write this A is really the disjoint union over vertices in our graph of A sub V. And A sub V is this. Oops, V dot X. And the V goes in front. So for each V, we get all of the structure of a ring. And the ring of sets generated by all of them are also fibered over the unit space. For the sake of posterity, I can get rid of it. Okay, let's just quickly analyze this this kind of thing. Let's see. So let's say let U be one of these ultrafilters. And let's let A and B the elements of U. Right, so set to that ultrafilter. So we know that we can write A as a disjoint union. I'm just saying finite. That's EI, where the EIs come from capital E. And B is also a finite disjoint union of, say, FJ. Anyway. Well, being an ultrafilter means that exactly one of the EIs belongs to U, and likewise exactly one of FJ. So there exists unique I and J. That's the calendar. EI, FJ, U, and then of course their intersection belongs to U. Now, EI and FJ look like this. So maybe EI is alpha minus some union of A to P in a finite not lambda, E star. So many mistakes. There's so many mistakes to make, and I make all of them. Let's write Fj is gamma E star minus, again, a finite union of say delta U. Well, the intersection is non-empty. And so in particular, it means that alpha and beta meet. So either alpha is an extension of beta or beta is an extension of alpha. So e.g. beta alpha. And that means that EI intersect FJ really has to be beta E star minus some larger finite set involving the different pieces we drew out. Let's just call it a finite union, some beta K star, something like that. So now if you keep looking for smaller and smaller sets in the ultrafilter, we're just going to be continually extending our elements. So the end result is not so hard to check that we have two possibilities writing it this way. So then either of one or two. And one is that there is, I'll just call it X equal say E1 to in E infinity, such that the set of all principal right ideals defined by initial segments of X, so E1 up to EM n E star, or n in the natural numbers, is a filter base. U. Or there is some element, let's say alpha in E star, such that U is the fixed ultrafilter at alpha. Of course, it's really an ultrafilter base if it's a filter base for an ultrafilter. So the ultrafilter is defined by a particular infinite path. And this is again our division of the space attached to the graph into the finite paths together with the infinite paths.
So all these E's are edges, right?
Yeah, little e's are edges. That's just a convenient way to write a thing. So the not E star. So the space XE that we're describing is really the same as the space we talked about last time. Finite paths together with infinite paths. So this process, let me just go back one slide. Building our way up from principal right ideals to this ring of sets in ultrafilters to get our space. It's giving us back what we found in a more explicit way before. And this method can be.
Could I ask a question before you leave the slide? Could you say again why this I and J are unique?
Oh, yeah, so if you have a set in an ultrafilter, any two sets in an ultrafilter must have a non-empty intersection.
Right.
So,
I see,
yeah, so you can't have more than one of these in there. But it's also true that if you have a set written as a union of two sets, one of those two sets has to be.
Right, okay,
Yeah, that's why somehow the U was picking out exactly one of these.
thanks.
Yeah, so Richard, because that's exactly how we're building this infinite path, right? We're always extending our finding. So one comment I want to make here before I move on. That and this generality of ultrafilters. We've sort of lost something. Last time I pointed out that we defined the space, and within there's a natural notion of the maximal elements. And the closure of the maximal elements is what we call the boundary. And it's the restriction to the boundary that gave us our Kunz-Krieger algebras. So in this very general notion of ultrafilters in this ring of sets, we don't see what the maximal elements are. See maximal elements. Of course, in this case of the graph, once we reinterpreted those ultrafilters in terms of the graph, then we can talk about what are the maximal paths, which is what we did last time.
So by this, you mean that we need to use the axiom of choice to construct these ultrafilters?
No.
So what we don't.
Oh, okay. So yeah. So this is from my lecture on Monday. So if you look at the finite paths, infinite paths clearly cannot be extended. They're maximal paths. Now, a finite path might be extendable, but if its source has no edges coming in, then it is not extendable. So the graph might have sort of, what do they call them? Leaves or dangling vertices that don't have anything coming in. So those finite paths would also be maximal. So the maximal elements are the finite paths that begin at a source and the infinite paths. And if we close up that collection, what we bring in are the paths whose source is an infinite receiver. This is what I would talk about. This, it's not a subtle point, but it's something people often miss, is if your graph does not have finite degree, finite in degree, then the set of infinite paths will not be locally compact. You have to include the vertices that admit infinitely many edges in. So that's why we have this general idea of look at the maximal elements, take their closure to get what we think of as the boundary. But we have to analyze the ultrafilter picture a little bit more in order to identify what that would be. That isn't quite a case-by-case situation. Not for each special thing we look at, but there'll be large classes where we can say something about. So, this making sense? Okay, so now I want to.
Make sure that I understand here. What we mean by ultrafilter is defined as a filter such that if A union B belongs to the filter, then either A or B belongs to the filter. Instead of the other notion of saying either for any subset A, either A or A's complement belongs.
Okay, so because we don't have complements in a.
Yes, exactly. That's what I meant.
Given any set, not any set, either the set, let's see.
Finite union implies one of the members belongs to the
If
filter.
it's not in the filter, then there's something in the filter that's disjoint.
That's equivalent to what I guess.
Yeah.
This finite union implies one of the members.
But I think the definition I was taught is it's a maximal filter. contained it properly in any other filter. There's another way.
We shouldn't expect that, given any filter, there is an ultra filter containing it in this setting. Yeah, okay,
That's actually the choice.
yeah, sure, okay.
Okay, so this is actually. Okay, so what I want to do now, so I've given these examples coming from directed graphs, from certain monoids, submonoids and groups. Now I want to move to the large abstraction as far as I'm willing to go at this point. And to make this clear, I want to come back to the left regular representation idea that we talked about, say even for just the free monoid. So Y is so this I sub L, say from F2 plus into the bounded operators on L2. A representation by isometries. So this is almost a silly question, but let's just write out what it means. So let's look at IL of some element. And to check that it's an isometry, we'll multiply it by a vector. So what does a vector look like? It looks like, well, let's use a vector from a dense linear manifold. So say the sum I equals 1 to M of say CI delta beta I. Typical element of, and let's look at the square of the norm. Okay, so now we know that the representation just multiplies each beta I by alpha. Okay? And then we'll write it using the inner product and use the Hermitian property to expand it out and use what we get sum over I and J. We get CI, CJ conjugate inner product of the basis element at alpha beta I, inner product basis element at alpha beta J. Yeah. Well, if this is an isometry, we should be getting the sum of the squares of the norms of the moduli of the CIs. Right? So this equals sum on I absolute CI squared if the following, so alpha beta I equals to alpha beta J.
Something like.
Yeah, it implies beta I equals beta J. This for all. Of course, we can take any betas we like. So it's really saying in order to get this isometric property, we need left cancellation. So the P property of F2 plus is left cancellation. So I realized that apart from Nika, I forgot to mention all the people who worked on this idea and sort of built it up from the beginning examples. So let me just start listing names. So we've already talked about Nika. After Nika, it was really on Locke and Rayburn. who studied this and pushed it into many places. Rayburn. And Marie Exel, of course. Shinley and Kuntz. I may not have the order proper here. Of course, lots of other people. So it was Shinley, I think, who really said, look at the regular representation. And that's where we have to draw all our intuition from. Yeah, it's interesting. So really all of this work until more recently followed the Kuntz-Krieger idea of defining our C-star algebra using generators and relations. So even though, you know, Nika's idea and Lee's idea really almost had more to do with this this other structure, this Nika covariance, which doesn't refer to this specific. I guess in the early examples, the two methods were so close that people really didn't see that there were different things going on. Okay, so I think it's a remarkable fact that only left cancellation is necessary to make the whole thing work. So directed graphs, this free monoids, the bounce, all these things examples we've had have much more structure than is necessary to do this. So here's the context in which,
In particular, it could be not even a submonoid of a group.
correct. And it doesn't have to be right canceling. And it could allow non-trivial inverses. All that matters is the left cancellation. But in fact, we don't even need a monoid, as we saw in the case of the directed graphs.
What is the intersection between these structures and inverse semigroups?
Well, so I'm going to show you actually. In fact, that's exactly coming up in it. My new friends in inverse semigroups have been beating me over the head trying to get me to use their language for what is obviously the right way. So that is, yeah, and just a little bit. Let me describe these objects, and then the inverse semigroups will be. But I hate it when people do that in the talk. So let me just tell you, and then I'll put it up again later. So we started with these principal right ideals. And of course, you can push them around with the left action. Well, even more fundamental than that, the left multiplication, it's because of left cancellation that left multiplication embeds our monoid into the partial bijections of itself. Now, once you have those partial bijections, you have their inverses, and those together, the inverses generate an inverse semigroup of partial bijections, and that's exactly.
And that's what you mean by we don't even need this monoidal structure as long as there's this embedding of the left multiplication into the partial.
Well, so the multiplication, there's some algebra structure we're using, the multiplication.
Yes.
The monoid is too strong. Well, for example, the path category of a graph is not a monoid, it's a small category, and that's really the general context. So let me just put this up. So I guess I feel I have to make this quasi definition. So a small category. It's a set, which I'm just going to call lambda with. And now I'll just list all the stuff we know. So there's a distinguished subset we call the units. We have maps R and F standing for range and source from lambda to the units. And of course, if you restrict either the range or the source map to the units, it's the identity there. And then we let lambda upper 2 be the composable pairs, so-called composable pairs. That's all say alpha beta in the Cartesian product of lambda with itself, so that source of alpha equals range of beta. And then we have multiplication from the composable pairs. And of course, lambda 0 to units multiply like units. So I think every time I talk about this, I say that I don't actually know the correct, precise definition of a small category. So we all know what a category is. A small category is just a category that has the objects form a set. But this is really what we have. It's
An internal category in the category of sets.
sorry.
An internal category in the category of sets.
Okay. So I maintained it called a category at all. It's a fundamental algebraic structure that deserves its own name. Because when people say category, I think something much, much more grand and ineffable. But that doesn't this name. Let's see. So
There is some question on chat. Small equals morphisms form a set.
Yeah, that's precisely the lambda. The lambda is the morphism set in this definition.
well, let's see. So
It's already required to be a set.
you can correct me. I thought that in a category, for any pair of objects, the morphisms between them is supposed to be a set.
Not really.
No, so what was here is called locally small category.
Yes. Locally small means.
But in this
And also objects.
everything is okay. So this is then
So this is really
objects are a
algebraic.
set,
Yeah.
and all the morphisms between all pairs of objects is a set as well.
Well, if you care about the foundational issues, in order to talk about smallness, you need to fix a universe beforehand. And everything is with respect to this universe.
I'm leaving all the foundation.
Yeah, we don't care about that. It's okay.
So the answer is locally small means objects form a set.
Okay, small.
So notation has changed since I was in the first year of graduate, but that's all right. It may depend on which book you read.
It's also this U small, where U is the universe. Forget that.
The universe is finite.
Yes.
No, okay, the answer to the question is I don't know correct use of terminology.
This is good enough. Yeah.
This is
Yeah, sure. For our purpose.
okay. Now, it's an algebraic kind of object because we have this multiplication. So we have a left action. Of course, it's only partially defined in the sense that a given element of lambda can only act on those elements with which it's compatible.
So sorry, there's an extremely stupid question. What do you mean lambda 0 multiply as units?
Right, so if you, so if
Compose the unit model.
so if you compose a unit with something. you-
Either on left or on right, they always
It means
not
it
change anything.
multiplies without changing the thing you multiply.
Okay,
And so
okay.
this was supposed to be a joke. I tell my students that the joke is like a theorem. Doesn't matter how you tell it as long as you can explain why it was funny.
Wait, yes.
Narratives would require that the jokes come from the book. They actually be funny when you tell them. Okay, so I won't write out this, it's the usual thing, just using the multiplication. But the key thing is that, well, maybe I should write it, right? So what do we have? We have alpha takes, all elements of lambda whose range equals the source of alpha and sends them to things whose range is the same as the range of alpha. We're sticking alpha in front. And these maps are one-to-one if and only if lambda is left canceled.
This is the same thing as saying every morphism is a monomorphism.
I've gone around in circles in this a couple of times. Because I know the word monomorphism is a technical term. Doesn't always mean, but I'm thinking.
It means like X compose Y equals X compose Z, different only.
What means left cancel?
Yeah,
Cancellation, monomorph.
Yes, and these means they're monomorph. So that's what we need to put ourselves in the kind of situation where this stuff I've been talking about works.
So groupoid is a small category where every morphism is an isomorphism, and the left cancelable small category is a small category where every morphism is a monomorphism.
Yeah.
Okay. Yeah.
Very good.
I can memorize it now.
yeah.
One-sided version.
Yeah.
So you can ask, does your left cancellation small category embed in a groupoid? And not always, right? Just the same way that a left cancellation monoid would be not embedded. So you know, it's somehow a very different structure, even though the definitions are quite close. Okay, so cancel a small category. I just write LCSC. Left cancel a small category. So now if lambda is a left canceled small category, then our left regular representation, right, from lambda into bounded operators on L2 of lambda actually maps it into partial isometries. And that's the same proof that we gave for isometries in a left cancelled monoid, except that now the domain is not the whole Hilbert space, it's only.
Is the definition of the representation, regular representation of this LCSC category? Because for partial isometries, you can compose them only if they range and source projections.
So this is not a
It's not an.
There's no composition on the right side.
it's just this.
Yeah.
Which element, which bound operators are we getting? We're always getting partial isometry.
Usually, if we speak about representations, we have some model.
This
is better other structures into this structure, but partial isometry do not.
I see your criticism. So this is our left regular representation. This is just identifying something about the image of the representation. It's contained in the partial isometries, but these don't have a good algebraic structure.
But I think the composable morphism in lambda will be mapped to composable partial isometry.
Yes.
Yep.
Yes.
Oh, yeah, right. So it's a nice sub thing of this, but this, well, it's not.
Subset is nice.
This is not so a sub thing of it is no information. But it inherits, the multiplication structure from lambda because it's represented.
And this generalizes the monoidal case because the monoid is just a category with one object, right? If you like that. Okay.
And in that case, we get isometries.
Yes.
Here. And it's because we don't get isometries that in general, partial isometries are badly behaved as a set. But you're right, we're getting a nice subcollection.
Okay.
That does compose. Okay, so what are the crucial properties of the regular representation? Right, so what do we use instead of the Nika covariance that we had for the monoids? Like that was the extra structure that monoids had that let us define a useful C-star algebra, define a good local compact Hausdorff space for them. So I'm going to just imitate what we did before in this very general context. So this will look very much like what we had before. So we, if alpha is in lambda, then we get this partial bijection S of alpha lambda. And actually the range of that map is all things that begin with alpha contained in R of alpha lambda. So it's a partial bijection. And then, of course, we have alpha inverse. Because of the left cancellation. So is this where I do this? So now we let I be all compositions of these kind of maps. So this is instead of all say alpha 1 inverse beta 1 to alpha n inverse beta n, where alpha i's, beta i's, that's our inverse semigroup. Now, let's call typical element of the inverse semigroup phi. So what does phi act on? Well, we have to be able to begin with sticking beta n onto something. So this acts on things whose range is the source of beta n. So E maps source of beta n lambda. Where does it go? Well, the last thing we've done after maltreating whatever element of lambda we started with is we remove alpha 1 from whatever we had before. And that means that what's left has to end where alpha 1 began. So this maps to the source of alpha 1. Or it's not mapping onto this. This is the domain, and this contains the range. Yeah. And of course, the range of phi. It's just all things that can be written. Oops, that's one. That looks like this, right? So start with anything in lambda, range, put beta n on. If that result extends alpha n, you can remove alpha n and move on to the next one. So you only want to put in things from lambda that survive this entire process, and then you get out some others. This is the idea. In the case of the graph, we saw, maybe I'll get to that later.
Can the domain of phi be empty?
Sure, this could be empty. Right, so it might be that there's nothing in lambda that you can do this sequence of on. Right, each time you compose two functions, you have to, the domain might shrink based on.
So in this case, I will get a partial bijection mapping empty set to empty set. Okay.
Zero in the inverse semigroup. So a set like this is called a constructible right ideal. This is Lee's terminology. So for a general lambda, these can be very complicated. And so that's why a specific example you might try to work with might be difficult to analyze because you have to think about these could be of arbitrarily long length and. Okay, so now I'm going to imitate what we did before. I'm going to change letters from E to D. So I want this to be all the constructible right ideals. So in fact, this set actually has some nice structure. It's closed under intersection. And then we from the Boolean closure, which I just call the curly D, the set of all E minus union 1 to I. Differences of constructible right ideals. And then the ring of set A is all finite disjoint unions. AJ. So in fact, then A is the ring generated by D0. And you can also characterize it. A is the ring generated by the principal right ideals. And these maps that we have, set of all theta inverse. In other words, the smallest ring of subsets of lambda that contains all the principal right ideals and is invariant under these maps. So it's not too hard to check.
And then you're using the same construction using ultra filters.
Yeah. So and also the same as so this range of the map phi gives us a filtering these things over the unit space. So all of these objects are actually filtered over the unit space. So all fiber, I guess, is a better way of putting it. So you see-
Excuse me, can I ask a question?
Yeah, go ahead, go ahead.
Why are the unions disjoint?
I chose to use only disjoint unions here. But if you start from this collection D0 that's closed on intersection, and you try to construct the smallest ring that contains it, you'll find that every element can be expressed this way. So certainly A contains unions that are not disjoint, but every element of A can be written as a finite disjoint union of sets from this collection E, which is itself formed from the collection D0 in this specific way. So it's just a way of describing the typical elements of the ring A. And that's useful sometimes, but you're right, there's no reason why you have to use disjoint.
Okay, thank you.
Welcome, thanks for the question.
So in a sense, in this D, you can remove intersections.
Yes. Yeah, I didn't mention it. if you can assume that the FIs are subsets of E just by taking intersections with E. I try to stay away from the screen with my hands, but can't do it. Okay, and as you mentioned, the next thing we do is look at ultrafilters. So yeah, so we let so I'm going to call it lambda. So this is now not continuing previous notation. This is a new use of the asterisk. Okay. Lambda star instead of all ultrafilters. Maybe I should just explain. So a directed graph is given by a set of vertices and a set of edges. So in order to make a small category, we have to use the finite paths. So we denote that E star, indicate that the length of the path is arbitrary but finite. That's sometimes called the path category of the graph.
I think in Backlin's book, they call it the free category generated by the graph.
Okay.
Something like that.
Yeah. So an operator
Without the drawing.
path category seems to be a common notation. But yeah, I grew up in a very small garden. I don't really know the names of the plants that are.
But it's interesting because you can iterate this operation. So I wonder what happens if you are starting from a category. You forget that it's a category, it's regarded as a graph. You construct this free category, small category generated by this graph.
So how do you think of a category as a graph? So,
Of course.
so same range in sources before
Yeah.
and just
A very big
You
directed
simply
graph.
forget the composition
okay, so if
and regard as elements.
so you
And this-
only compose using source and range.
And this free category of the graph is the left joint of the forgetful functor mapping your category.
I don't know. Well, so you've
Yeah.
lost any internal structure the category had.
Yeah.
So
You can get a even
nothing to do with what.
more, yeah.
So yeah. Now the thing is that if you start with a category, it may not be built up out of minimal elements.
Yes,
There may not be anything like edges. So the idea of a there's no need to concatenate things to build something larger. It's all sort of within there. There may not be any notion of a elementary thing like you can do for graphs. So I'm just going to use this single star to indicate the biggest set. We want to work with all the
We suggest that this sister algebra would be stable under this iteration of.
Well, I think the C-star algebra you get at the second stage will have nothing to do with the C-star algebra at the first stage, because you've lost all structure in the category that would have, that's the important part of what we're dealing with. So I don't know what would happen in that case. You get some sort of a sequence of graph algebra.
In a category, we're setting a second free construction. Well, the first free construction is a quotient of the.
Yes.
Free construction. But I'm not sure on the C side. On the C side level, it should be something that the iteration should embed into the one without iteration, but that should not hold. No.
Yeah.
It's weird.
Hard to say because it's hard to say what the functoriality is.
Yeah. Weird.
Yeah. So it might be worth playing with data. You could think.
Okay, iteration at the moment.
Yeah, no, it's I don't in a different ballpark. I don't know what that is. Let's see. I don't want to see.
Will we put the topology on this?
Yeah, so I should say what topology is. But I didn't connect the topology back in the graph case earlier, but let me explain what it is now. So it's very it's sort of the obvious thing once you sorted through all of this stuff. So if you take a set capital A in this ring A, we let I'm going to denote by A hat all ultrafilters that contain it, right? So these are compact open sets that form a base for the topology. Totally disconnected. Locally compact Hausdorff topology.
If our category is a poset, then this should coincide with this topology of stone, probably.
I think that must be the case, though I'm not familiar enough with the process to sort it out in my head right now.
Or even Boolean algebra.
So I think it's definitely stone theorem.
I'm struggling to see why A hat is compact.
Well, no, so you could use these to define a topology and then check that A hat is from.
Yes.
So there's another way to do this. I thought I wouldn't have time to do this, but maybe I'll show you this.
Oh, I think.
It's a little bit cute. So an alternative way of seeing this topology or seeing the space altogether. Think of that set capital A, its characteristic function is just a bounded function on lambda. This is a bounded function on lambda. It's in blue L infinity of lambda. Now, since the ring A is closed under intersection, these are closed under multiplication. So the span of these it's a star algebra inside of little L infinity. So we can take its closure in the norm.
And then this spectrum is okay.
We call this B lambda. And this lambda star is exactly spectrum of B lambda. And this A hat is exactly the support of this continuous function on B lambda. B lambda.
I have a question. Sometimes if we start from a graph, you obtain a sister algebra of a graph, which is the deformation of some nice space. But here you obtain a totally disconnected locally compact Hausdorff spaces.
So
How to reconcile these two kinds of topology?
The C-star algebra coming from a directed graph really has to do with a certain totally disconnected Hausdorff space. So if you look at, say, O2, when Kunz proved that O2 was simple, he did it by finding a UHF algebra inside of it. But the space is then the diagonal of that UHF algebra, which is the usual Cantor set. So I'm not sure what space you're thinking of that isn't totally disconnected.
I remember from the proof of Szymański, there's an idea that there is precisely there is something of kind of a Cantor set, but I cannot see how this totally disconnected locally compact Hausdorff space topology, how this is related to the theorems of this Cantor setting.
It's complicated. If you take the three monoid on two generators, really that's the path category of the graph. That's one vertex and two loops. And so if you follow this construction there, the Cantor set you're getting is just the boundary of that tree in the usual way. So this is just a generalization of that construction.
So there's the idea of the Cayley graph somewhere here, and boundary of the scaly graph?
No, that's, the calligraph is somehow special to the free calligraph.
Yes.
Then you're just getting this tree.
But in this special case, it is the topology of this boundary.
Yeah, it's, the boundary is Cantor set in the usual way, and that's exactly what you get.
Okay.
Well, no, in the sense that, right, so you have this tree in the first quadrant, and the Cantor set is the boundary. Well, the space lambda star is the boundary together with the tree itself. Right, so it's the compactification of the tree. And then that will give us what we call the Toeplitz algebra.
Yeah.
And if you restrict to the boundary, you get the actual. And we'll have the same phenomenon here, though. This will define the largest C-star algebra, Toeplitz version. And that's why we have to identify the maximal element somehow. Get the boundary, and then we can restrict to get what we might call Kunstkrieger algebra. Now, in this generality, there will be lots of closed invariant subsets of the space between the whole thing and the boundary. And many of them might be very interesting, maybe more interesting than a boundary even. It depends a lot on this. So here's an example. Suppose you consider the left cancellative monoid. And suppose it's order, the order we get from, the left multiplication is directed.
Okay.
So then the boundary consists of a single point. There's a little bit more you have to assume. But in that case, so suppose your monoid is a submonoid of a group, generating a submonoid of a group. In that case, the C-star algebra of the boundary would just be the C-star algebra of the group. So it's maybe not interesting in the sense that it doesn't see the any structure that this monoid has on its own. So you might want some larger set than the boundary, maybe not the whole thing. I think I'll be able to show you an example of that, but maybe not today.
Haven't talked about the boundary of this construction.
Right, that's right. So of course, we can't talk about what are the maximal ultrafilters. Those are exactly maximal. So one has to dig into this a bit and give a more explicit description of the points in lambda star based on something else, where we do have a notion of order, and we can talk about maximal elements. So I guess I don't want to do that in the complete generality. Because most of the interesting examples have a different way of describing them, which is easier to work with, and is really what I want to get to next. So I worked out a way of describing this so you can see the boundary, and other people have too. But almost every time I've given a talk, someone has said, "Oh, hasn't so-and-so already proved this 10 years ago in the following?" It's one of those things that many people are coming to from different directions. Okay, so
A completely dumb question. Can you tell me one more time, why do you use this notation lambda star? So lambda star is ultra filters in A because lambda is what?
So lambda is this left cancellative small category.
Okay.
And I need a name for the locally compact Hausdorff space we attach to it. And so I chose this. Okay, shoot me if you must.
No.
That was my choice. And I don't actually know what other people, I'm sure there's lots of other. Okay.
And how is A obtained from this alpha?
So this.
Yeah.
Okay, so we look in lambda at the
Sorry, I said alpha, I meant lambda, I'm so sorry.
That's right. So within lambda, we can look at these principal right ideals, right? And we also have the bijective maps gotten by multiplying with elements of lambda and the inverses of those maps. So you look at the smallest ring of subsets of lambda that contains all the principal right ideals and is invariant under all these.
Okay, I remember you said it. Okay. Yeah.
And the fact that you have to be able to invariant in these maps means you actually have to build these constructible right ideals as well.
Okay.
And then so yeah, so just giving a description of the ring that's more specific than that general characterization is what I put on.
You know, this is the drawback of a digital whiteboard you mentioned yourself. I mean, there's just one, here there are three. So I cannot look back to your previous slide and to remind myself.
I think
Yeah, thank you.
the appropriate pun is.
You could ask. to Show the previous.
Yeah, but it disrupts the flow.
I'm happy to move back.
No, it's okay. You did, I simply didn't memorize it. So.
Okay, so let me very briefly mention the C-star algebra. Okay, so I decided that I would not try to talk about locally compact groupoids and C-star algebras of groupoids because it's a very useful way of building C-star algebras, but it is a bit technical and I don't think it'll be useful to talk about. So let me just give you a rough idea of where the C-star algebra comes from. So
Have a separate lecture course
right.
about C-star algebras of points by DJ, who is in the audience.
Yes, that's what you need. You need a bit of a course.
Yeah.
So to go from lambda to a C-star algebra. Well, we look at star representations. So this, I think, and again, let me emphasize the most important first step when you're confronted with such a lambda is finding this locally compact Hausdorff space. So if you're given something by generators and relations, then you have to play with it like a puzzle, try to tease out the structures. So this recipe is more complicated, but it is a recipe for finding the space, and that gives us the basis for doing our analysis. Okay, so we look for star representations of this commutative C-star algebra as bounded operators. This is just commutative C-star algebra representations. And then for an element alpha in lambda, and I'm not really telling you how to do it. Find partial isometries. What do you call it? Pi alpha? No. Let's see. Pi alpha. Okay, let's call this pi. And we want
Is it a regular representation?
no, this is just we're looking for
What is H? Arbitrary?
some Hilbert space. Yeah. So we're looking for star representations like this. So we want them to be a representation on the functions on lambda star. We want it to give us partial isometries V of H. And what do we want? We want so the initial projection of pi of alpha should be the image of. So remember, we have these chi sub elements of our ring, right? So this should be so this V of alpha is the same cylinder set notation I used with graphs. Right? So all this is really it's like the principal right ideal generated by alpha, but it's in lambda star, not just in lambda. So that's the range projection. Okay. And this is incorrect. Source of alpha.
C0 lambda star is just your P lambda above, right? So just describe it to you directly using P lambda.
Yeah, yes, I mean, it's exactly
You should be
right. So because C0 of lambda star is exactly B.
yeah. So we can just use these chi-A's to be the same alpha.
Yes, as long as you remember that they're now functions on this space instead of functions on lambda.
Yeah.
So simple means two different things. And the range projection. That's the image. But so I'm thinking now it's functions on lambda star. I'm not using this notation. exactly because I get mixed up where I'm thinking of the elements, but you're right, we could easily do that. And we also wanted to be homomorphism, like so.
What is this? Chi Z of alpha or R of alpha?
No, there's no R.
Chi Z of in the last line.
This one here.
Yeah, Z of alpha or Z of R of alpha.
It's not R of alpha, it's actually alpha. Remember, when you want to multiply by alpha, you multiply by anything whose range equals the source of alpha. But what you get is something that actually begins with alpha.
Okay.
So it's not everything that ends where alpha ends, it's only the things that actually have alpha at their beginning. So that's, that's the actual range of the partialized geometry. Even though it's a sub-projection of what we would get if we use the range of alpha. So this is really domain and range, not domain and codivariant.
Excuse me. What is exactly H? It's L2 of the space?
No, so H is some Hilbert space, and we're looking at representations of the commutative C-star algebra on some Hilbert space that also admit a family of partial isometries that represents lambda and has the right source and range.
But H is not determined by lambda or the space?
No, because what I really want to look at is the universal C-star algebra generated by representations that respect the structure we're talking about. So L2 of lambda is one example where this happens, but there can be many others. And
So it's a definition of a representation
yeah,
in a Hilbert space by partial isometries.
and
But
the
sorry, if L2
sorry,
if L2 of H is if L2 of lambda is an example, what
Yes.
is the measure?
So the issue is that there may be representations that are not weakly contained in the left regular representation. So to get a universal C-star algebra, in general, it will be bigger than what we get just from the left regular representation.
Does the regular representation correspond to something like the reduced version?
That's actually subtle.
It's not.
It's subtle, yeah. So I mentioned that one can also build a groupoid on this unit space that describes the situation. And so you can look at the full and reduced groupoid C-star algebras. And it turns out that the reduced groupoid C-star algebra is not always the same as the left regular C-star algebra. So you have to look at sort of bizarre examples to see that happen.
And there's the issue of groupoids, right, versus groups. Am I right? Or can you have such a funny thing for groups as well?
Well, so this, for a group, we just get the group C-star algebra out of this. It's really the lack of at least some inverses that give this structure something more interesting than what we have from a group. So if your category is a groupoid, then there's nothing here beyond the groupoid C-star algebra. But if it's not a groupoid, then there's this extra stuff that comes from, there's this direction you get from multiplication when you don't have inverses. And that's really what's underlying all of this stuff, is capturing the information there. So maybe I'll just put the last sentence of this thought over here. So the Toeplitz algebra of lambda, I'll define to be that universal I'll just say for such representation. So, and the point is that using the order structure coming from this small category, we find this locally compact Hausdorff space, and we get this commutative C-star algebra in addition to just the category itself. So this is just saying represent the category by partial isometries, but they have to behave properly with respect to the functions as well. And that's the analog of the Nika covariance in this general context. And so that's why we get a C-star algebra that actually is tractable as opposed to some enormous unwieldy that just has to do with the multiplications.
And is it obvious that the sister algebra exists?
Yeah, because all the generators,
Because it's partial isometry.
well, yeah, and then this commutative C-star algebra is fine.
And you have an example given by H equal to L2 lambda.
So now it's possible to describe the algebra by generators and relations in the same way that the Kreuzer-Krieger algebras are defined by generators and relations. Generators will be built out of the elements of lambda, and there are many different ways of building such algebras. So, no, maybe I'll just end it. Maybe I won't continue on to the next topic today, because
But you still have 9 minutes. So.
well, then I could, yeah. But I would just like to put in my own personal philosophy about this stuff is, you know, watching the development of graph algebras from Kreuzer-Krieger case to arbitrary directed graphs. I was mathematically aware when that was happening. And you could see that people said, well, what do we do if the graph has this strange feature? They would try this and try that. And eventually, of course, these guys were really smart. They figured out what the right generators and relations were. Then the higher rank graphs were introduced. And only the most basic kind were defined in the beginning. And the variations that happened there are much more subtle and complicated. And it was really hard for people to figure out the right generators and relations. Of course, they did. It was Rayburn, Sims, and Yeats paper.
Kumji and Pass.
Well, Kumji and Pass gave the original definition.
Okay.
But the definition that really stood the test of time was in the paper by Rayburn, Sims, and Yeats. I was tortured to watch them do this. You know, it's like watching somebody lift the enormous boulders to build a wall. But why should you have to guess the relations for your C-star algebra? There should be a way of extracting it accurately so you don't have to guess. And that's what this recipe does. Starts with a category, which is what a higher rank graph is anyway, and gives you a recipe for building the C-star algebra without defining generators and relations. And then afterwards, you can find generators and relations by imitating what those guys did in the other cases.
So you're saying that this formalism you are describing to us right here encompasses as a special case this high rank.
Oh, yes, yes. Those are very special examples. Those are actually cancellative small categories. With no inverses.
So that looks.
And they have this degree functor with unique factorization. They're very, very special.
Yeah.
And very hard to describe.
Somehow this would be making the life of studying higher rank graphs and their C algebras somewhat much easier.
That's exactly what I wanted to say, yes.
Yeah, I think the hard part of higher rank graphs is getting your hands on them. We try to, if you want to draw a directed graph.
I've seen the definition, but I can never memorize.
Yeah, I want to try to not to talk about higher rank graphs in these lectures, this will take too long.
Yeah.
But they're, you know, the relations you have to impose to satisfy the definition are very strong. And you have, if you start drawing things, now you're forced to put in something else to make it behave properly. And then that makes you put something else on. And it's hard to control this process in describing it. So, yeah, this is supposed to make, not so much make it easier to study higher rank graphs, but easier to write down interesting examples without having to jump through students. And what I hope to do next time is describe some interesting examples that you get by just drawing something and seeing.
So you get these examples and they are clearly examples of your formalism, but it's not clear how they would be presented as higher rank graph algebras.
Well, they're not higher rank graphs.
Are they even not? Okay.
Well, let's see. So, of course, the C-star algebras are. That's what actually why they're interesting examples is you recover things that are known to be even graph algebras, but in a unusual way. But the underlying structure is definitely not a high rank graph.
Mhm.
So it's a left canceling small category.
So let's just finish by discussion. We bumped into the following very simple sister algebra. The sister algebra of a multi-pullback quantum odd sphere. You just take the tensor power of a Teftis algebra and divide it by the tensor power of compact operators. Okay. And from the non-commutative topology point of view, it's clear how why it should be a sphere, because classically, if you take a multi-disk and would divide it by the interior, of course, take the boundary of a ball, and then that's a sphere. Because ball is even dimensional, the sphere is all dimensional. Okay. And then in order to get some nice properties of this sister algebra, I remember we described it, and by we I mean Aidan Sims and David Pask as higher rank graph sister algebra. And then we had some technology and we could prove some isomorphisms. And one of the things, because Richard Ness was also on board, so he theta twisted everything. And so somehow, what was the usual tensor product, now say these partial isometries that would commute when you have a tensor square of a Teftis algebra, now they theta commute. And of course, when you have more of them, it would be given by some matrices. So I'm wondering, but then of course we go beyond higher rank graph sister algebras. They are twisted higher rank graph sister algebras. So would the twisted higher rank graph sister algebras also be possibly examples of this formalism?
So I don't know at all, but I would guess that you could define some sort of twisting in this setting. That's more likely.
So it's more likely
That would be
okay.
like this.
Okay.
This would be a more general version of that.
Yeah, of course, it gets twisted.
So I'm not sure that how to make this notion of twisting, whether it could just be done or if you need strictly the kind of lambda.
Because in the higher graphs, it's kind of obvious. You have different colors for your generators, your edges, and then you have to say, different colors and what community.
Yeah. So, for example, the higher rank graphs are distinguished by having this homomorphism into n to the k. It's very strong.
Yeah, this degree map
factorization property. Now, if you take a left canceling small category, there may be homomorphisms into a discrete abelian group or discrete abelian monoid. They may not be as strong as that as having this. But anytime you have a homomorphism into an abelian group, that gives you an action of the dual group on the C-star algebra. And so you can look at fixed point algebra and things like this. So you can decompose the C-star algebra using these kind of maps. And there might be many such maps, and you can maybe use them in different ways. Whether there's something short of a unique factorization degree map that will still give you something, you might be able to build some sort of twist using information like that without having to have the full-blown higher rank graph structure. But I've never thought of it. That's very interesting.
Okay. And because you mentioned fixed points, so I immediately have to ask you, so where is the gauge action in your picture?
Well, so it depends on having a homomorphism into an abelian group, which may not exist.
Okay, so in general, you don't have it.
There may be none. But lots of times there are many different ones, and you might try some combination.
I have another question. If instead of taking this left cancelable small categories, I'm taking a category that is cancelable on both sides.
That's even better.
Yeah, now if I'm taking the opposite category, I reverse all the arrows and do the same sort of construction which is allowed. And that's let's say that Topis algebra in this setting of the opposite category have some relation with the Topis algebra.
Yeah, so I don't know what relation there might be, but I know that they aren't necessarily the same.
Oh, no. Yeah.
Right. So that's the Kunz-Krieger algebras, they are the same, but that's very special.
Yeah, the category is very special.
So if you go to infinite matrices or infinite graphs, then very much they can be different.
So self-duality of the category.
So I don't know the answer to your question.
Maybe another question is, we know that the opposite algebra of this topic algebra is not isomorphic to this topic algebra, or
But would the opposite algebra correspond to the opposite category?
no, that should not be the case, but I'm asking.
No, because if that were the case, then I could definitely answer no.
Yeah. Yeah, I'm wondering whether this system algebra is isomorphic to its opposite algebra or not.
Yeah, no, that I don't. I've not ever
Quite probably,
Yeah,
because changing
So there. A long time ago, I
picking
remember
or arrows.
hearing about various results along these lines. I just don't know what is stated, what's true for C-star algebras and their opposite. When are they isomorphic? I don't know. People do know, some people know, but
because if you take this cancellation property on both sides, there is this clear choice of left and right, and you are choosing the left. And there's no reason to.
also you could always use the right vector representation.
Yeah, yes.
Right cancels.
Then
It's like for the groups, you can use the left vector representation as right. Yeah,
It's like considering category of modules, for instance.
maybe
but it's a good point. Besides, if there are two, what's the difference?
you will get to
I don't know. I don't know.
you will get very different system algebras.
Yes.
Might not be clearly related.
Yeah, my guess would be that they are different, but I'm just.
On the level of the category, the comparison with its dual
Yeah,
or opposite,
like that. Something like
something
that.
like.
Okay, so maybe it's a good point to wind up, okay? So let me stop recording and we adjourn for 2 days. Stop recording here. Yes. Stop recording.